a great round of applause right now. So our next speaker is Ian Hall, who is based at Manchester University. Again, I may have guessed at Ian's talk title, and I think he was debating whether he was going to talk about waning immunity today. So are you talking about waning immunity, Ian? Or
no. No.
But I guess I should say that Ian's group are currently working on a waning immunity model. So if that is something you are interested in, you may want to follow up with Ian at another point regarding the work they've been doing. And I'm pretty sure someone will be giving a talk from your group at some point next term on it. So yeah, just to let you know, that is something else Ian's group are doing. But with that, I will pass over to you, Ian, and I'll let you give your own talk title.
Yeah, thanks. That's fine. Let me just share my screen. Yeah, I mean, on the on the waning immunity front, I think Francesca. Okay, why did that not go full screen? Francesca will be giving one of the elevator pitches tomorrow, and so waning immunity may come up then, or it may not. But yeah, we have been looking at various aspects of waning immunity, and the model that I'm about to talk about can be extended. We've thought about how to extend it to incorporate waning immunity, and I will touch on that. So Kira, you're not completely out on a limb there. I'm going to talk about our work for sort of a collaboration between JUNIPER and Protect really here. So this is, Protect is one of the national core studies with a focus on transmission funded by the Health and Safety Executive. And we have another postdoc working with us here, Jing Si, who is sort of working on the dose response and within host modelling work, and I'll sort of show how that relates to some of the JUNIPER work we've been doing as well. So this is really sort of two synergistic projects that are really quite important. So why are we looking at dose response? Well, we have, or why does the within host model potentially important? Well, we have a virus pootling around in the environment, and it passes over one person who is completely fine, and then it hits another person. And that's probably not as part of the sort of that isn't a magical process. That's a sort of probabilistic process. And so it would be helpful to have a model for that so we can understand dose response. Now, when we're developing a model for the within host dynamics, we started off, as many other groups have, with this piecewise exponential model where sort of given an initial dose, your virus within your body starts to grow exponentially, and then at some point in time it decides to start decreasing, and the mechanism for that is fairly handy wavy. We can sort of retrospectively create mechanisms for that about the adaptive response, the innate response, or whatever, but it's more of a sort of convenient, simple mathematical function that adequately describes what we see in some of the biological data, and it's a useful starting point. But then we moved through, we did a lit review at the start of the Protect work to see what other models people had come up with, and we found what I'm going to be calling the Goyle model, and I'll give a link on the next page there and explain what that is. But that was a paper that sort of develops a more sophisticated model with various assumptions, and we have taken that in two different directions. One is we've tried to simplify it so we can fit it to some of the human challenge data with fewer parameters, and we have also adapted how the the adaptive response kicks in and does things, and that's work with Jonty Carruthers in UK HSA. And I haven't had time to proofread every slide here as I've been creating them, and occasionally PHE might slip in, and apologies if there's a rogue PHE at some point, but yeah, where it says PHE, I mean UK HSA. Now, the Goyle model was published in eLife a few months ago, and this is very much not our work. We have just taken a version of it, and I've put the equations from the publication here. What you essentially have is you have some susceptible cells, some infected cells that interact with, like the susceptible cells interact with the virus, free viral load, and then the infected cells die off due to the innate response with the parameter delta, and then the adaptive response. And the adaptive response is given by those three final equations. It's sort of a lagged response that finally kicks in with the sort of the logistic function there on the I state. Now that's a really nice model, and they've done a really nice analysis there, and so we didn't need to sort of improve that model in any way or add features to it apart from testing some of the assumptions. And so what we were able to do is create a simple Goyle model where we just set I proportional to V rather than have a separate V state. And that works because the kill rate in the viral the V state is quite fast, so it doesn't look that different when you plot the full model. And you can also see with the parameterization with the best fitting parameterization from the Goyle work, the adaptive response basically switches on. It's sort of on or off, and so we can just put a Heaviside function on the adaptive response and assume K is small, which is the boost to the innate response, and you can come up with a much simpler model that hopefully we can calibrate more easily to the human challenge study data that we have. And then the model A there is the piecewise exponential, just to have the equations down on the slide for reference. And so that's sort of the non-mechanistic model, or the simpler model. The adaptive model, I haven't put the equations down there, but that involves a sort of logistic growth on the adaptive response. And that, yeah, as I say, that's being worked on by Jonty as we speak. There's a few considerations here, and these are considerations for further work. We've got another 6 months or 3 or 4 months on the Protect project, and yeah, these are probably longer term issues. So if you look at that Goyle model or the simplified Goyle model, what is driving the peak to viral load is the depletion of susceptible cells. This is kind of it's very similar model to an SIS model or an SI model, and so that's probably not surprising. But I think a lot of people, when you're speaking to them, assume that the decrease is because of the adaptive response or the innate response rather than the depletion of susceptible cells. And so is the model misspecified, and have we missed something important there about the replenishment of susceptible cells and what timescale that occurs over? So we need to think about that a little bit more as a group. There's no space here, and space here is within the human body. There's no spatial aspects, and so local saturation might be important, and so we need to be careful on that as we extrapolate from the model. And also the location, the route of infection might be important. So if we inhale a dose, that gets into our lung space and does whatever it does in the lung. But if it was a fomite transmission route, then you're rubbing your eye. Does the movement around the body work in quite the same way or is there this local bottleneck? And so I think that's probably a much longer research. That's probably a PhD in its own right, looking at these local rates and the migration. But those are some of the considerations we need, and we need to be aware that the model is simplistic. And so, but why is it useful to have a model of the viral load over time? Well, one use, and Carl will probably talk about this in his elevator pitch later this morning. One use, and I don't want to steal too much of his thunder, so I won't go into too much detail in case he is using this material. But one use is the testing. So how good are LFDs and PCR tests? So we can use these models to look at the effectiveness of testing, and then layer on top of that assumptions around LFD adherence, to compare different strategies for the testing regimes. And these testing regimes are the adult social care testing regimes, where we do two LFDs a week, one of which is tied to a PCR test. And so that's the status quo. And then you can look at various combinations of tests accordingly. So that's an important application, and the viral load dynamics over time, present in the model, use the piecewise exponential, but we will work under JUNIPER to sort of use some of the more mechanistic models to look at the impact there on the assumptions. And then we can come to dose response. And so here, so those viral dynamics over time give us some mapping of the infectivity of an individual. But that person's wandering around the environment they live and work in, and meeting people or interacting with people and infecting them. So, and the person that they are potentially infecting will have some sort of probability of infection, so a dose response given a dose they receive. Now, we looked at this over the years when I was in UKHSA or PHE, and we looked at it for bacterial infections. And one of the problems is that a lot of the animal challenge studies for dose response, and this is an anthrax study that's on the graph, the triangles, non-human primate study. It shows they dose the animals up and they get a probability of infection or not. But pretty much any statistical model you can dream up will adequately fit the data. But often we want to then extrapolate to lower doses to see what a low dose regime might look like. And extrapolating outside of the data is very hard. Well, it's easy with a model, but it's very hard to know the model is accurate. And that can be a problem, especially when you've got orders of magnitude difference in your model specification. And so we've got to be very careful there and just think about what the models are actually doing and the sort of hidden mechanisms or the assumptions that are being made. And so, again, I stress this is leveraging bacterial infection work, but there is a sort of school of thought. You move from the statistical convenience models, then you move to semi-mechanistic, and you can add complexity accordingly. And in the interest of time, I'm not going to dwell too much on this, but basically you can have a few assumptions that sort of underpin this. So you can have an individual infective dose, that there's some magic tolerance level that you as an individual have, and the model comes along and challenges you, and if you're one organism less, then you're fine, and if you're one organism over, you're infected. And that is normally then assumed to be log normally distributed, and you end up with a sort of probit model Or you have these sort of competing risks where you're challenged with a number of organisms, hit with a number of organisms, and one of those might eventually germinate, and then you end up with that, and then you end up with an exponential model, or you can have these birth-death processes. And so you can fit an exponential model to that data. You end up with this sort of alpha parameter, but the alpha is really a composite of the ratio of clearance and germination, in the language of an anthrax attack, sort of removal and infection for a virus. And we can start to extend that through at a population level, and you can have fun with hypergeometric functions, making various assumptions about how the in-host variation on the germination rate and the clearance rate evolves. You end up with a Kummer function. If there's over dispersion in the dose, so rather than it being a well-mixed room, or if there was a bit of clustering in space because that's where the dose was, then you can control for that, and then you can allow for sort of the stuff not quite getting to the part of the body that it needs to get to, and so on. And so you can have these fairly arbitrary complexity on the dose response, and we looked at that in this risk analysis paper. And why is that important? Well, the exponential model assumes that the bacteria or the virus is homogeneous in the atmosphere. The breathing rates are all homogeneous across the population, and there's very little variation. So those are very easy assumptions, but they may be wrong. And if we do look at those hypergeometric functions, then you can start to see what might fit adequately to an experiment, because you have controlled for all those things and you've tried to homogenize things. If you put it over a human population in the wild, so to speak, perhaps where there is this structure, you'll start to get lower attack rates. So that even the ID50 might move around. So we can start to tease around what is happening at the sort of dose response. And bringing this back to SARS, these graphs are not yet fitted to the human challenge study, so they're illustrative, but what they show is the figures on the right are the sort of the dose response function for various doses received, and then the left-hand plot is the probability of infection given the used dose response function. And the Hill function on the top is what the Goyle study used as the dose response. The bottom plot is the competing risk. And so you can start to see that there are differences in the assumptions we make. And so the assumptions about the mechanisms might be important, but you can also see there's parametric differences as well. So we could see quite short, sharp infectious windows. And so people are mostly infectious on day 3 of their infectious period, or it could be quite drawn out. And and that sort of drawn out period, probably there would be a parametric basis for that. And so we do need to be cautious on the assumptions we're making, and not sort of throw just the sort of first mathematical or statistical function we can find and sort of justify those assumptions a little bit. And if we can't justify those assumptions, we probably need to think about chaining these models together to look at the appropriate uncertainty. And that's work we started to look at on the Crystal Cast project before it was derailed because of COVID a few years ago. So just to wrap up, hopefully I'm not overrunning wildly. Yeah, the assumptions we're building as we're building these models are key, and yeah, many statistical models can explain data, but this is where the mechanisms could be important as we extrapolate away from where we have data. And we are currently working with some of the human challenge data that is available on the Protect project to calibrate these models and to sort of look at the uncertainty and how good these assumptions are. And I will stop there. As I say, this is work like Jingxi's done a lot of the sort of modeling extensions and the calibration. Carl was working on the testing effectiveness work on Protect and a previous project, MRC project, looking at gig workers. And yeah, thank you to Jonty as well for the work he's done on this within UK HSA. And I will stop there. Kira.
Great, thank you very much, Ian. Does anybody have any questions? If not, I would like to ask one question, Ian. So I should also say, I meant to say within host modelling, not waning immunity. So sorry, Ian. It's I blame a teething baby. So sorry, I see Feng has a question. So Feng, do you want to ask your question?
Yes, thank you. It is possible to combine this waning host model with time since infection model to provide the effectivity.
I assume you stopped there rather than just get cut off, but from internet. But
infection model,
yeah,
we need to provide the time, the infectivity, which depend on the time, which one, yeah, probably we can draw this quantity from the waning host model.
Yes, I mean the simple answer is I think yes. I mean Francesca is probably better placed to comment on that, and so certainly Francesca and Lorenzo are more expert in the time since infection modelling. I mean on the one thing but yeah, I mean, conceptually I think that would be a useful goal to test to look at that in more detail. I mean, one thing I forgot to say as well on the waning immunity is that currently the models we have are just looking at the acute infection stage, but clearly if we can start to get a biological understanding of how the adaptive response wanes over time and how those target cells, the susceptible cells, are replenished over time, then there's every potential for looking at longer term dynamics and using this to test waning immunity assumptions as well. But that's yeah, that requires a little bit more understanding on the biological mechanism.
Great, thanks, Ian.
Thank you.
So if anyone has any more questions, feel free to write them in the chat, and then we could try and get Ian to come back to them later, or come back to them in the panel session. So thank you very much, Ian.